Okay, so in the chat, I have pinned a link to this same notebook that you are watching right now. So you can follow with me everything I am saying and you can execute the cells. So welcome to this open source quantum software tutorial. This is the very first one, so we are going to talk about the basic stuff about quantum computing and how to make quantum programs using a couple of frameworks. So welcome again, my name is Claudia, and anytime you have a question, please let me know. I am going to try to be attentive to the chat, and also if you want to open your mic, it's just fine. So the beginning, what is quantum computing? This is a new way or a different way of make computation that is going to take advantage of quantum mechanical phenomena, such as superposition, interference, and entanglement. This phenomena is not available in the common computation. We are going to call it classical computation in order to make the difference. Classical computation is going to be the one that we are used to, the one that uses our current computer, our current laptop. And quantum computing, quantum computation is this new one that we are going to study. So in the same sense, and as a complete analogy with classical computation, we are going to need to define quantum algorithms in order to solve problems, right? And for that, we are going to need to create quantum circuits. And these quantum circuits are going to use quantum gates. Everything is in analogy with classical computation, right? So if you search in the internet for a quantum computer, probably you are going to find an image like this. This is just one example of a quantum computer. I mean, not every quantum computer is like this, but a lot of them are similar to these schematics. All right, so a very brief history about this. We started in the beginning of the past century, where the theoretical foundations were established. I mean, quantum mechanical physics arises in that moment, and a lot of foundations were established in that moment. So we wait until the decade of the 1980s for the idea of creating a quantum computing. One of the persons that make that proposal was Richard Feynman, and he said that if we want to simulate the nature, and the nature is quantum, so we need something that really simulates that. So that's why they propose a quantum computer. So after that idea was out there, some people started to develop algorithms, quantum algorithms. One of the most famous is Shor's algorithms. Another one is Grover algorithm. Uh, and it was only theory how these algorithms could work. But at the beginning of this century, in 2000, several companies started to develop actual quantum hardware. So companies like Microsoft, Google, IBM, and among others have created the several implementations of quantum hardware. So people are investigated and investing in this quantum technology. So today is a reality. We can access this quantum hardware, and we can program this quantum hardware. So how can we do that? Well, we have to our disposal some frameworks for that. So first thing, what is a qubit? A qubit is going to be the equivalent of a bit. So qubit is quantum bit. And in formal terms, it's a two-state, meaning has two levels, quantum mechanical system that, because it's a two-level, belongs to a two-dimensional Hilbert space. This means that we are going to need two complex numbers to represent a qubit. So we usually use Dirac notation to represent it like this. This is called ket. And this ket is a shorthand for a vector, a column vector of two elements. And these two elements, alpha and beta, are complex numbers, as I mentioned before. And we are going, this force us to use linear algebra. So in that sense, we are going to need a basis. The most common basis used is the called computational basis, that it is formed by ket0 and ket1. And the two vectors for that are the one shown here. So any quantum bit can be a superposition, some proportion of ket0 plus other proportion of ket1. So alpha and beta are called probability amplitudes because we are going to represent these proportions are percentages. So what is the probability of getting the zero state is going to be alpha, absolute value of that, and the square. This is the probability of getting probability of getting ket0. And the absolute value of beta square is the probability of getting ket1. So in that sense, we need to accomplish this normalization because the probability only could be 100% tops, right? So alpha and beta are probability amplitudes, and when we take this quantity, we are calculating the actual probability of getting one of the other bases. So because we can write any qubit in this form, we have a superposition of the two elements of the basis, 0 and 1. Okay, this is important. This always must be accomplished. And this is the definition of a qubit, which basically is a two elements column vector with these characteristics. Another way to represent a qubit is the Bloch sphere. This is just a representation. So we are going to take our generic qubit, as we saw before. And because alpha and beta are complex, so alpha needs two real numbers to express it completely, and beta also needs two real numbers to express it. So at the end, we need 4 real numbers, right? And it is really difficult to make a draw in R4. In that, because of that, we are going to make a transformation to a representation that we can draw. We are going to transform R4 to R3, and this R3 is the surface of a sphere. And after that transformation, we are going to have this representation in which the north pole of the sphere, this here, is where we are going to locate the ket 0, and the south pole of the sphere is where we are going to find the representation of the ket 1. And any qubit like this is going to be in any point of the surface of the sphere, like this, for example. So because of that, we can locate this point with two angles. This angle that is respect to the plus z axis, that is called theta. And the second angle is going to be this phi, that is respecting to the plus x axis. So with that, we have this new way of representing. Alpha is going to be cosine of theta over 2. And beta is going to be e to the I phi sine theta over 2. So this phi is called phase. So the phase is going to be that angle that is respect to the plus x-axis. All right, so phase is important. We are going to work with phases in the quantum algorithms. So we have this transformation, okay? And we have this representation. This representation works only for one qubit at a time. So we need somewhere to put these qubits. And this somewhere is going to be a quantum circuit. As I mentioned before, is a complete analogy with classical computation. So we are going to have something like this. Each horizontal line is going to represent the qubits. So in this example, we have 3 qubits. We are going to name the qubits from top to down, and the usual way to do it is start the index in 0. So because we have 3, indexes are 0, 1, and 2. All qubits start in ket 0 state, always. And we are going to read the quantum circuit from left to right, and this is how time occurs. This is a 1 qubit gate, because it's affecting only 1 qubit at a time. This is a 2 qubit gate, because it's affecting 2 qubits. In this case, it's affecting Q0 and Q1. And this other one is also a 2 qubit gate. In this case, it's affecting Q0 and Q2. And after we manipulate of our qubits with quantum gates, we are going to be interested in the result. And for that, we are going to measure the final state of the quantum circuit. So this is the symbol of a measurement. And when we measure, we want to save that result in some place. That's what this double line arrow represents here. Is saying that is saving the result in this register. This register in the bottom is a classical register. Here we are seeing that has 2 classical bits, and we are saving this one, the result of this qubit in one of the classical bits, and the result of this other qubit in another classical bit. So that is in general how a circuit works. But we are going to start with very simple ones. So we are going to work with Qiskit and PennyLane at the same time, so we can see how to write these quantum programs in different frameworks. So in order to install the frameworks, since are Python framework, Python libraries, we only need to do pip install and the name of the package. So if you install this package today, the version is going to be 1.4. This could change if you execute this cell another day, for example, in a month from now. And you're going to see everything that is needed to be installed. I like to install Qiskit with the extension of visualization, which installs also another packages that help us to visualize things. And we can install the other framework called PennyLane by using this instruction. The current version is this one, 0.40. And both frameworks can live in the same environment. So it is totally safe to execute these both shells. If you prefer, you can download the notebook and run it on your local machine, and it's going to work also. So, okay, we have the concept of quantum circuit. Let's make a quantum circuit. Using the framework Qiskit, in order to create this element, we are going to need an object of type quantum circuit. So we create it by indicating how many qubits we want. In this case, we are going to use 1 qubit only. We define this into a variable. And this other class called the state vector is going to help us to obtain the state of the circuit. When I say the state, I am referring to the quantum state that is represented by a column vector of 2 elements. And that's it. In this example, we are only creating 1 quantum circuit with 1 qubit and getting the state vector of that. Then finally, in order to see the information, we print the state vector and then we draw the circuit. This parameter only indicates that we want the drawing using Matplotlib. So what we have here, it's a very small quantum circuit with only 1 qubit. And we know all qubits start in ket 0. So at this point, the state of the whole quantum circuit is going to be ket 0, right? And we know that the vector that represents ket 0 is 1, 0. And this is what we are seeing here. So in this print, we are seeing the whole thing because this is alpha and beta, but alpha and beta are complex numbers, so the entire number must be 1 plus 0i and 0 plus 0i, right? And in Python, we represent the imaginary element with a j instead of a I. So this vector, this is one element, and this is the second element, is exactly this vector. That represents the ket 0. So the state of this is very small quantum circuit is correct, right? Is the ket 0. And how can we do this with PennyLane when it's a little bit different? It is common, it is usual to import PennyLane as QML. because if you search for any example using PennyLane, you are going to find this. So QML is the way that we are going to use this library. So we need to define a device. This device is going to represent the quantum circuit. In this device, we are going to specify how many qubits we want. PennyLane uses the word wires in order to refer to qubits. So when you see wires, it means how many qubits you want. Then the place that we are going to use to put all the things we want for the quantum circuit is going to be inside a function. This definition, called circuit PennyLane, is going to represent the object of the quantum circuit. And we are going to use this instruction that it is called a decorator in Python that indicates that this whole function is going to be decorated, is going to taking as a quantum circuit, as a quantum device. Because we are working with very simple things, there are quantum devices of this type, but we can use other types. But for now, we are going to use this one. And the only thing inside the function is that we want to return the quantum state. Which quantum state? The one that represents the quantum circuit. So when we execute the function, the result of that, because of this return, is going to be the quantum state. I am using the same name for the variable. So I print it. And I also can draw the quantum circuit. For that, I am going to use this function, draw MPL for matplotlib. And finally, show this figure. So it is almost the same with the specifics for PennyLane, but we are doing the same as in the previous example. So here we have only one qubit. In this case, the drawing only shows the index. And PennyLane is assuming a measurement at the end. I didn't specifically write it in here, but PennyLane is assuming it. But for now, we are not taking this into account. So I am asking for the quantum state of this quantum circuit. So at this point, because all qubits starting ket 0, is going to be ket 0. And this is exactly the state that we are printing here, corresponding to this print, which is 1 plus 0i and 0 plus 0i, right? Same thing. So here we can see the differences between Qiskit and PennyLane, but we are doing exactly the same stuff, creating one small quantum circuit with one qubit and getting the state of that. So, right, we have qubits, we have quantum circuits. We want now to manipulate the qubit in order to do something, in order to do calculations. For that, we are going to use these operations called quantum gates, which are unitary operators represented by unitary matrices that are going to be written according to some basis. The basis that we are using is computational basis, right? The computational basis, which is formed by these two elements. So these quantum gates are matrices. So the matrices must have the correct size, because we know that this is a column vector of 2 elements. So in order to manipulate that, we are going to need a 2x2 matrix so we can perform the computations. So this multiplication is valid. This is a 2x2. and this is a 2 by 1. So the result of this is going to be 2 by 1. Like is written in here. So in general, any qubit is going to be operated by a matrix that is a quantum gate. So the result of that is going to be a new quantum state, a new qubit of the same size. So we started with psi sub 1, we apply an operation, and after that, we are going to get the state evolved. And this is basically how it works. And of course, if we have more than one qubit, when we have one qubit, we have n equals to 1. But if we have n bigger than 1, for example, n equals to 2, so the size of the vectors are going to be 2 to the 2. The column vector it will have 4 elements, and the size of the matrix is going to be 2 to the 2 by 2 to the 2, right? A matrix of size 4 by 4, and so on. If we have 3 qubits, we are going to have 2 to the 3 elements, meaning 8. And if we have 4 qubits, 16 elements. And this is how we increase exponentially. But for now, we are working with just 1 qubit. So what we can do to a qubit? One thing we can do is to create a rotation around each axis. So I can apply one of these quantum gates, X, Y, and Z, that are called Pauli gates, that are based on the Pauli matrices. And this means a rotation of p radians around the corresponding axis. So for example, we have this is seen in the Bloch sphere. So if I start in ket 0, which is this, I rotate around x-axis. So I am going to end up in the one state, right? With this expression. I apply x to the ket 0, I end in the ket 1. And if I start in ket 1 and rotate around x-axis, I am going to end in the ket 0. So this first gate, X gate, is also called negation gate, because if I apply to 0, I end with 1, and if I apply it to 1, I end with the 0 state. And also it's called bit flip, because it's what it does. Changes 0 to 1 and 1 to 0. And the matrix representation of this quantum gate is this simple one. And we also have the rotation around y-axis. So I can rotate around y-axis, and if I apply y to 0, I am going to have the 1, but I have to include this phase of I. And when we apply y to the 1 state, we are going to have this flip. I'm getting the 0 state, but we need to add this phase of minus I. The corresponding matrix is this one. And third quantum gate in this family is around the z-axis. So in this case, when we rotate around z, if I start in 0 and rotate in that same angle and the same axis, well, I did nothing. I end in the 0 state also. But when I apply z to 1, I am still going to end in 1, but we are going to include a phase equals to -1. So the corresponding matrix is this. Okay, how can we do this with code? Again, we create a quantum circuit with only one qubit. This one indicates how many qubits. And now we can indicate that we want to apply an X gate by using .x method. And this parameter is the index of the qubit to which we want to apply it. So because we only have just one qubit, the only index I can use is 0 because we start counting from 0, right? Also, I can apply Y, and also I can apply the other gate set. In the same way as before, we can get the state vector of the entire quantum circuit. I mean, the state vector at the end of the quantum circuit. And we can print it and draw the quantum circuit. So let's see what is happening here. What is the state at this point? 0, because all qubits start in 0, right? So what is the state after this gate? Anyone? Okay, the state is 1. And what is the state after this other gate, after the Y gate? Do you remember? Hello? Is anyone there? Okay, it's going to be minus I get 0. And this is going to be minus I multiplied by this column vector. And this is minus I 0. And this is minus I 0 minus I and the 0 plus I 0I. And this vector is this one, right? So it's working. And how can we do this in PennyLane? Very similar. We are going to access the quantum gates through the main package that we call QML. So inside the function that helps us to define the quantum circuit, we are going to apply the X gate. This is the index of the qubit or the wire. Usually you can find also this notation, wires equals to 0, or as in a list, this is also valid. But because it's only one qubit, I can write down only the index, like in this example. So in the same way as before, I return the state, the quantum vector state, print it, and draw the quantum circuit. So the behavior is exactly the same as in the example in Qiskit. And the vector, the final vector state is exactly the same. because we apply only X and Y. What will be the state if we also apply Z? Well, you can check it by uncommenting the line and executing. Oh, okay, I forgot. Yes. My kernel died and I cannot run this, but it doesn't matter. You can check it by yourselves. So the Pauli gates are rotations around each axis by p radians. But we can also rotate by any angle we want. For that, we are going to use these other quantum gates that are called rotations. Rotations around X, rotation around Y, and rotation around Z. The corresponding matrices are these. You can use them in order to understand how the qubit is manipulated. In a moment, we are going to see how we can make the code for that. And another very famous gate is the Hadamard gate, which is really useful and really common because it's the one that helps us to gain superposition, equal superposition. So, for example, when we apply it to the ket 0, the result is another ket that we usually call ket plus, which is the superposition of 0 and ket 1. And the probability of getting 0 is going to be 1/2, right? And this is alpha square, and this is also beta square. So the probability of getting ket 0 or getting ket 1 is the same, 50%. The Hadamard gate is also rotation, but it's a rotation around a specific axis, an axis that it is between Z and X, this axis over here. So we are going to rotate in this direction and in this direction. So when we apply Hadamard to the ket 0, we end up over the plus X axis. And when we apply the Hadamard, the Hadamard gate to the ket 1, we end in the minus X axis. And this state is called ket minus. So the Hadamard gate is going to be used in several quantum algorithms. This is the corresponding matrix. And in order to apply them in Qiskit, we only need to do .h and the index of the qubit. And in order to apply the rotations that we saw, is going to be .rx, ry, and rz, like in this example. And here we are making a rotation around z by p/3. So in this example, what we are doing is we start in the 0 state, we apply X, this moves the state to the ket plus or the X plus X, and then we are going to make a rotation around Z by p/3. So the final state is going to be around here. This angle is p/3. Okay, so this final state is represented by this vector. And in Penny Lane, they're really similar, right? QML.h and the index of the qubit, and QML.rz, the angle we want to use to make the rotation, and the index of the qubit. So the result is exactly the same. So let's see an example using the visualization of the Bloch sphere. Qiskit provides a method that allows us to plot the Bloch sphere, which is this one. So we are going to start a quantum circuit with only one qubit, take the state vector. So we are doing this. One qubit, then we apply H gate, and then we apply R set gate. So at this point, we are calling the state psi 0. After H, we save the state again, and this is psi 1. And after R set, we are going to save the state in the variable psi sub 2, which are these. And we are going to use those to plot the Bloch sphere. So we already know what we need. We are going to see. The initial state is the ket 0 because every qubit starts in ket 0. After that, we apply the H gate, which let us the qubit in the ket plus. And finally, we apply the R set gate with an angle of P over 3. So this is the final state. This is the rotation around the Z axis. So in general, we have phase shift gates. These gates are going to affect the one state only. As we can see here, if we apply the phase shift gate to the 0 state, it's not going to affect it. The result is going to be the ket 0 again. But if we apply it to the ket 1, we are going to add a phase. That's why it is the name. A phase equivalent to e to the I to the angle that it is the parameter. So we add this phase to the state 1. This is the matrix representation in which we can see that it is only affected the ket 0, the ket 1. And for certain values of the parameter phi, we are going to have specific names of the gates. For example, when the parameter is equals to pi over 2, this is the parameter phi. The name of the gate is called S. And we can note that S is the square root of Z. And we can note that Z is equals to P of pi, right? Because the rotation is by pi radians. So when we take the square root of Z is equals to S, which is equals to a phase of pi over 2. And we can also do a rotation to the other way around. All rotations so far, when we talk about rotations, the rotations are counterclockwise. But if my parameter is negative, minus. So the rotation is going to be clockwise, right? And when we have this case, the name of the gate is S dagger. This symbol here, it's called dagger. And this means that we are applying the rotation to the other way. These are the corresponding matrices. And we are having rotations around Z by these angles, pi over 2 or minus pi over 2. This represents S and S dagger, respectively. And if the angle is pi over 4, the name of the gate is called T. So here we can notice that T is the square root of S, and we already know S is the square root of Z, so it's the fourth root of Z. And if we want to rotate to the other side, we can have the T dagger, which is going to be the rotation with minus pi over 4. So the gate T is also very used in several circuits, and only means we are rotating by pi over 4 radians at a time around the Z axis. So how can we do this in code? When using Qiskit, we have defined all the functions for all the cases. We can do dot P, which is the phase gate. And we need to specify the angle and then the index of the qubit. So, for example, the S gate is going to be applied by dot S and the index of the qubit. But if you want the version dagger of the S dagger is going to be applied by dot SDG. DG is an abbreviation of dagger. And this is the index of the qubit. The same thing happens with the gate T. We have dot T method and dot TDG method in order to apply the T dagger. So this is a simple example. In order to see the rotations, I start applying an edge gate so we can start here. So because all our rotations are outside gate, we can have visualizations of this pi over 7, then pi over 2, then pi over 4, then pi over 2, then pi over 4 to the other side. And this is what is doing this circuit, rotating a little bit to both sides. So in Qiskit is very direct by applying these methods. In PennyLane is not so direct, it's a little bit different. For example, the phase gate is called phase shift, has a longer name, but this is the same as the P gate we saw before. We indicate the angle and the index of the qubit. And to apply the X gate, we have QML.S and QML.T, but the dagger versions, we need to calculate the corresponding adjoint, which is the same as a dagger. So we take the S gate, for example, and take the result and send it to the method adjoint, QML.adjoint, and this is equivalent of applying S dagger. Same thing is for the quantum gate T. We are going to take the application of the T gate and then calculate the adjoint, and this is going to be the T dagger. At the end, of course, we can corroborate that this quantum state is the same for the case of the Qiskit code. And the quantum circuit is also the same. Here we can notice that the name is different, but it doesn't matter. In Qiskit was the name P. Here the name is RFI, just a curiosity, but it's the same gate. So that's it for the first session. Do you have any questions? I know it's very basic. Maybe you already knew all of this, but we need to start and establish how we are going to work. Next session, we are going to talk about 2-qubit gates. Well, not 2-qubit, 2 or more qubit gates and bigger circuits. So the states are going to be more complicated. So when we have that, we can work with quantum algorithms because we are going to already know how the quantum gates are affecting our quantum state, represented by a quantum circuit. So yeah, the real fun is going to be together with the quantum algorithms. So if there are no questions, see you next time for the second session. I hope the notebook that I share with you is useful. Please try to make your own experiments with both frameworks, both Qiskit and PennyLane, so you can familiarize how they work. So far, the difference is not very big, but at some point, the difference are going to be more notorious. Yeah, thank you for being here.